When we learned about stoichiometry, one of the things that we discussed is that you can take the grams of a substance and then you can use the molar mass and you can convert those grams to moles. Okay, for example, if you have 43.0 grams of N2, you can say there's 28 grams in 1 mole of N2, and then you take 43 divided by 28 and you get moles of nitrogen. And once you have moles of nitrogen, then you can do stoichiometry with that using the balanced equation, etc. Well, we know that one of the components of the ideal gas equation here is moles. So if we start with PV equals nRT and we solve for moles, which again is N, we have to divide by RT. So the moles are going to equal PV over RT. And just like the moles we would get here by dividing by the molar mass of nitrogen, if we know the pressure of nitrogen and the volume and the temperature of nitrogen, we can also get moles of nitrogen or oxygen or whatever, any gas that they're talking about here. So once you have those moles, just like when you take 43 divided by 28 and you get 1 point whatever moles of N2, you're going to take the pressure, the volume, R, and temperature, and you're going to get moles here as well. And then you can use those moles and do stoichiometry, just like you could when we started with grams. So really, there's two different ways for you to get to moles. You can convert grams to moles using the molar mass, or you can use pressure, volume, and temperature, and the gas constant here, and you can also find moles. Okay, let me show you what that looks like. Okay, so example number 1. Safety airbags in automobiles. I don't know if this is true, but initially they were inflated by nitrogen gas generated by the rapid decomposition of a compound called sodium azide, which is NaN3. Okay, and so this would heat up really, really quickly inside the, so you would, your car would hit something, it would signal something in the steering column. This would heat up really, really fast, and it would produce a large amount of nitrogen, which would fill up the airbag before you have the time to come forward and hit the steering wheel. Okay, so if an airbag has a volume of 36 liters, and they want it to be filled with a pressure of 1.15 atmospheres, and again, around room temperature. Again, great question. How much sodium azide do you need? Okay, so when we do this problem is, again, they're giving you information about nitrogen gas, but they're asking you about sodium azide. Okay, so the nitrogen, again, notice nitrogen is the only gas here. Solid, solid. Okay, so the pressure is referring to the nitrogen. Okay, and plus you can see a chemical equation there. You may have to balance that chemical equation, but again, the main way you know, oh, this is involving stoichiometry, is the fact that they're asking you about one thing, but they're giving you information about something else. So the first thing we're going to do is we're going to use the pressure, the volume, and the temperature, and we're going to find the moles of nitrogen. So notice here I used N equals PV over RT, the pressures in atmospheres, the volumes in liters. There's my 0.082 liters atmospheres, Kelvin mole on the top, and then there's my temperature in Kelvin. Okay, so that means that in order to, again, fill up that airbag completely at a pressure a little bit higher than normal atmospheric pressure, at again normal atmospheric or normal temperature, you need about 1.69 moles of nitrogen. Okay, so to produce 1.69 moles of nitrogen, we have to figure out how much NaN3 we need to start with. So we take our 1.69 moles of N2. So just like if we had converted our grams to moles, we now have moles. So now what am I using here? Obviously, to do stoichiometry, I'm using the balanced equation. And I'm going from moles of N2 to moles of NaN3. So moles of N2, 3 of them, to 2 moles of NaN3. So there's my 3 and 2 there. And then I go to the periodic table. I look up the molar mass of NaN3 at 65. And then I just do the math. So that means that the steering column will need to have about 73.2 grams of sodium azide in it. So when again it heats up really quickly. It produces a huge, that 36 liters of nitrogen gas. Your airbag fills up just to the right amount, not too much, not too little. Okay, and so when you hit it, your body slows down much slower than it would if it slams into the steering wheel, which again, obviously much, much safer. Okay, another example. This one isn't done for us here. So ammonium sulfate, an important fertilizer, is prepared by the reaction of ammonia with sulfuric acid. So part A, we need to balance the equation. So right away I see one nitrogen here. Here I see two nitrogens. So I'm going to need to put a 2 there. That makes 6 hydrogens plus 2 more is 8. There's 8 hydrogens. And then SO4, SO4. So all we needed was a 2 in the front of that NH3 right there. And then B says, calculate the volume of NH3 needed at 42 degrees Celsius and 15.6 atmospheres to react with 870 grams of H2SO4. So it says, notice in part B, you're given the grams of H2SO4, and you have to find the volume of NH3. So this process is pretty similar to the last example we just did, but we're going to start by taking the grams of H2SO4 to moles and then do the stoichiometry step to get moles of, what are they asking us about? NH3. So we're going to go 870 grams of H2SO4. H2SO4 has a molar mass of 98.1 grams per 1 mole of H2SO4. And then from the balanced equation, we can see that 1 mole of H2SO4, 1 mole of H2SO4 reacts with 2 moles of NH3. Now again, if I'm doing normal stoichiometry, a lot of times I'm going to keep going here and I'm going to get grams of NH3. But remember, to get the volume of NH3, again, starting with PV equals nRT, to get volume, I've got to divide by pressure. So volume equals nRT over P. I don't need grams. What do I need? I need the moles of nitrogen, or of NH3, not nitrogen. Okay, so now I go to my calculator. So I'm going to take 870, divide that by 98.1, and multiply by 2. And that is 17.7 moles of NH3. Okay, now I've got moles, great. I've got temperature, great. I've got pressure, great. I have everything I need to now solve this problem. So again, V equals nRT over P. So our moles are 17.7. R is 0.082 liters atmospheres over Kelvin mole. The temperature is 42 plus 273. I believe that is 315 Kelvin. And then our pressure, 15.6 atmospheres. And again, if we've done it right, we better only have units left for volume. So moles over moles, atmospheres over atmospheres, Kelvin and Kelvin. What are we left with? There's my liters right there. Okay, so 17.7 times 0.082 times 315 divided by 15.6 equals 29.3 liters of NH3. Okay, and that's our final answer there. Okay, one more. Again, progressively trying to make them a little bit more challenging. So in example 3, cellular respiration occurring in our bodies as glucose reacts with the oxygen gas we breathe, producing carbon dioxide in water. So we have to write a balanced equation. So the glucose reacts with oxygen gas. Oh, that's why we need air to live. It's because we need that O2 so our bodies can do cellular respiration. Interesting. CO2 and H2O. So let's see, we've got 6 carbons, so 6 carbons, 12 hydrogens, so put a 6 there. And now we have, let's see, 6 times 2 is 12, plus another 6. We have 18 oxygens on this side. We already have 6 accounted for here, though, so we need 12 more. So a 6 goes there as well. Okay, so part B says calculate the volume of CO2. Now, before I do this, you might want to pause it and see if you can do this yourself. This is pretty similar to that last one that we just did. So see if you can do it yourself and then unpause it and then watch me do it. So 24.5 grams of glucose reacts complete with excess oxygen. They want the volume of CO2. Okay, so it looks just like that last one. So 24.5 grams of C6H12O6. And then again, the only thing you can ever do with grams is convert to moles. So there's 180 grams in 1 mole of C6H12O6. And then we're going to go to the balanced equation, 1 mole of C6H12O6. And then what they're asking us about CO2. So we're going to go to 6 moles of CO2 from right here. So 24.5 divided by 180 times 6 equals, that doesn't seem right. Oh yeah, it does. Okay, 0.817. 0.817 moles of CO2. And then again, the volume of CO2, just like the last problem, nRT over P. So 0.817 moles, 0.082 liters atmospheres over Kelvin mole. The temperature, 37 plus 273 is 310 Kelvin. And 0.970 atmospheres. And again, moles cancel, atmospheres cancel, Kelvin cancel. We're just left with liters. So 0.817 times 0.082 times 310 divided by 0.970 equals 21.4 liters of CO2. And you know, when you breathe, what comes out of your lungs when you breathe is, of course, CO2. Okay, so you've got to get that CO2 out of your body somehow. Okay, and that's one of the ways the oxygen goes in your lungs to react with the glucose, and then the CO2 and the H2O have to both come out. Okay, and you breathe both of those out. Obviously, some of the water when you go to the bathroom comes out as well. So. Okay, part C. What mass of water is produced when oxygen gas at 785 torr at a volume of 2.5 liters is at a temperature of 25 degrees Celsius with excess glucose? So now they're asking us about the mass of water, and they're giving us information about oxygen. So this is a bit similar to the first one we did, where they give us the pressure, the volume, and the temperature, so we need to find moles. So N equals PV over RT. So the pressure is 785 divided by 760, and that gets me to atmospheres. The volume is 2.50 liters. R is 0.082 liters atmospheres Kelvin mole. And the temperature, 25 plus 273, is 298 Kelvin. Okay, so 785 divided by 760 times 2.5 divided by 0.082 divided by 298 equals 0.106 moles of, and again, we're talking about oxygen. So these are moles of oxygen. And the reason that's important is because now we have to use that balanced equation. So now we're going to take 0.106 moles of O2. And now we need to go back to our balanced equation here. 6 moles of O2. And then they're asking us about water. Make 6 moles of water. So 6 moles of O2, 6 moles of water. And then they ask for the mass of water. So 1 mole of water has a mass of 18 grams. So 0.106 times 6 divided by 6, those just cancel. So we're really just multiplying by 18 equals 1.90 grams of H2O. Okay, and so stoichiometry can be used just like it can with regular stoichiometry, but rather than using grams to convert to moles, you can use PV equals nRT to get to moles.